Okay, we start. We are now at 46. Okay, we check it out. Flip-flop applications we are talking, huh? Right. Okay, for example, you look at this circuit, the two input AND gate. Detect the input sequence. This circuit, you cannot detect the input. Let's say, you know, 1 and 1 here, output will be 1, right? But whether the one at A first or the one at B first, you cannot tell, right? The circuit cannot detect the input sequence. As X become a 1, regardless which one is a 1, it will be a 1, a 1, and a 1. But what we want, let's say we want you to do something. How to have X is equal to 1 if A have a 1 first, and then later B have a 1. A first. How to have a X equal to 1 if A go high first, and then B goes high sometime later. Alright. So how? Very simple. What you can do, we want when A and B, A are 1 first, output will be a 1, right? Let's say, okay, you put a connect A to J, connect B to the clock. This is a positive trigger, yeah? Positive trigger. K is connected to ground all the time. Okay, so you see, A is connected to J, B connected to ground. You see the clock, clock is, B is fit to the clock, K equals 0. So X can only change when positive trigger at B, right? Okay, now check it out. Let's say your B connected to the clock, right? Let's say A here already, come in already. B, let's say this B connected to the clock input, right? Let's say now B now become a 1. Do you see that? Now, here at this one, that's trigger, right? Something happened, right? You see, A is already a 1, right? So your X is equal to 1. You see that? A before B, Now, okay, for example, your B a 1 already, but A still a 0. What happened? Then output is a 0, right? You see that? Let's say A is a 1, but A later, then you come, A become a 1 after B, therefore X will remain a 0. Yeah, like that only. We just connect to the chicken flip-flop, and we can use this to achieve the result. You no big deal, right? B connected to clock input, yeah. At this point, okay. When the time comes, A is still a 0, leh. All right. So your output is still a 0 at your. Okay. Very straightforward. Now, parallel data transfer. Let's say this, you got a combination logic circuit, X, Y, Z. Yeah, here. This is a D-type flip-flop. You know what's a D-type flip-flop, right? D-type flip-flop. Then when the clock come in, input 1, output 1, input 0, output 0, output follow input lah. Okay, so all the clock connected together. It's a negative trigger. So when the time comes, whatever data in X, Y, and Z will be reflected out at your Q1, Q2, Q0. Like that only. Let's say the data here, maybe from a computing system, the data is changing all the time. So when the clock comes, negative trigger, so whatever data here will be reflected out here. Right. Nothing more than that. This is a parallel data transfer, one of the applications. This one. Frequency division and counting. Let's say you can see this. They all connect at toggle mode. Output connect the clock input to the next stage. Output connect the clock input next stage, or in toggle mode. Right. So it's for the clock counting. So this part later you will learn. We will talk about that later on. So frequency division and counting. So okay, let me jump the gun a bit. When we have this kind of connections, toggle mode, the clock here, let's say the frequency here is F. I tell you, the frequency at the output will be F upon 2. This guy is more or less like a divided by 2 counter. Here also, let's say you got a frequency here, there's a toggle mode. What happened to the frequency here? The frequency here will be this frequency divided by 2, half. What happened? There's also toggle mode, the frequency here. What happened to the frequency here? This will be half. So let's say you got a frequency here divided by 2, divided by 2, divided by 2. Let's say this is a frequency here. What happened to the output here? The output will be divided by 8, right? Divided by 2, divided by one stage, another stage divided by 2, another stage divided by 2. We talk more in the next few pages of the PowerPoint. Yeah. Okay. We stop here.